Okay, so here is our lecture video for our section 10.3, Apply Properties of Chords. And just as a little reminder, back to our definitions we did at the beginning of a chapter, a chord is a segment with the endpoints on a circle. So it's just a segment inside the circle. A few facts to remind ourselves is any chord divides the circle into two arcs. So any chord we have, any segment inside this circle is going to divide the circle into two different arcs. The diameter, which is a very specific chord that goes through the center of the circle, divides a circle into two semicircles, two perfect half circles. And any other chord just divides a circle into a minor arc, which we know is smaller than 180 degrees, and a major arc, which we know is greater than 180 degrees, and we can see here in this picture. So those are just a few reminders before we get into what this section is all about. We're going to start here with our first theorem of the section. And it's just like a theorem about chords, and it tells us that in the same circle or in congruent circles, two minor arcs are congruent if their corresponding chords are congruent. So the big thing here is the corresponding chords are congruent. So if we have congruent circles or we're just in the same circle like we see over here, if these segments, these chords are congruent, these arcs, so the arc from A to B and the arc from C to D, are also congruent. So moving on to our first example. So in the diagram, circle P is congruent to circle Q. We can see that, just as a reminder, these radii are congruent. So we know that those circles are congruent. And they tell us that FG is congruent to JK. So we have two congruent chords, and the measure of arc JK, so this arc right here, is 80 degrees, and they want us to find the measure of arc FG. Well, our last theorem told us that if we have two congruent chords, we have two congruent arcs. Well, since FG and JK are congruent, we know that their arcs are going to be congruent, so we know the measure of arc JK is going to be congruent to the measure of arc FG, which means that it also equals 80 degrees. So that's just using that theorem to say, okay, we have two congruent circles, two congruent chords, which means we have two congruent arcs. So why don't you guys go ahead and try one example like this on your own. Just got one little problem here. Pause the video and try this one on your own. Okay, so looking at this example here, if the measure of arc AB is 110 degrees, so here's arc AB right here, and they tell us it's 110 degrees, find the measure of arc BC. So what we are looking for is the measure of this arc right here. So just the part of the circle, that arc right there. And it's the same circle, so we're looking at that chord right here and this chord right here, and they tell us that they're both 9, which means we're in the same circle. We have two congruent chords, which means we have two congruent arcs, which means this is also going to be 110 degrees. And we'll keep a lot of the questions when it comes to this very basic, like this one right here. So keep moving forward. Another new term that we might see is bisecting arcs, and we've seen this word bisecting before. It just means to cut into two congruent halves, two congruent pieces. It cuts it in half. And if arc XY is congruent to arc YZ, so we're looking at our picture over here, this small portion of the arc XY is congruent to YZ, then point Y and any line, segment, or ray that contains point Y, so this point right here, any radius, diameter, chord that goes through that point, we say bisects arc XYZ. And it just cuts it in half. Two congruent pieces, cuts it in half. Again, we're just using that bisecting term that we've used a lot already this year. And that leads us in to our next set of theorems. Our first one here, if one chord is a perpendicular bisector. So perpendicular bisector, just a little refresher, perpendicular means 90 degrees. Bisector means cuts in half of another chord, then the first chord is a diameter. And our second theorem, before I kind of get into explaining, is if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. And this is just the converse of the first theorem. So basically, if we have a chord that's bisected at a 90-degree angle, so we see that it's bisected and intersects at a 90-degree angle, we can say that this chord right here, QS, is going to be the diameter. And if we look down here, using the converse of that same theorem, well, we see that they intersect at a 90-degree angle, and the fact that they put this point here tells us this chord EG goes through the center of the circle, which means it is a diameter, so we would know that that must bisect using that converse of the theorem. So again, it's splitting it into two congruent pieces. Pieces of the chord are going to be equal to each other. So this example is kind of more of a complex thinking about it example. We're not going to see a bunch of these on our own, but let's think about it. We are gardening and we have 3 bushes arranged as shown. Where should you place a sprinkler so that it is the same distance from each bush? Circles like to use the same distance from everything because that's what a lot of properties of the circle give us. So to start, I'm just going to kind of redraw our picture over here, and I'm going to label these bushes A, B, and C. But I'm just going to do it over here so we can kind of see the drawing a little bit better. Here's bush A, bush B, bush C, something like that. And I'm going to go ahead and connect them all with a segment to start. And being that we're talking about perpendicular bisectors, I'm going to go ahead and draw the perpendicular bisector the best I can to both of these segments I just drew in. So I'm going to take my ruler and we can kind of eyeball it a little bit. Just kind of find the middle of your segment, eyeball it, try to draw on a line that's 90-degree angle, and we know we drew in the perpendicular bisector, so I know that those two pieces are also congruent. I'm going to do the same thing over here for this other segment, kind of find the middle, go at a 90-degree angle, and I know I split it into 2 congruent pieces. So all I did was draw in the perpendicular bisectors. And by doing that, in the theorem we just said, if we treat these as chords, the pink lines here that connected the bushes, since they are perpendicular to this intersecting line right here and they cut in half, that lets me know that the purple lines I just drew in are actually the diameter of a circle containing all of these points. So if we think about it, there's this circle that goes around these bushes like so, and I just drew the diameter in with those purple lines. Yes, it's a rough drawing, but that's okay. And they want us to find where should we put the sprinkler so that it's the same distance from each bush. Well, if these are the diameter, or these are both the diameter of the circle, that means where they intersect is the center of the circle, which means that intersection point is where it's going to be equal distance. Now that's just really diving deep into that theorem that we're talking about. Again, I'm not expecting you guys to be able to draw a picture like this and explain that all on your own. That's more of like, let's think about it type of idea. And the examples that you are going to see more of with this theorem look something like this. So we are going to use the diagram of circle E to find the length of segment AC and then tell what theorem we used. Well, circle E, E is the center because they tell us it's circle E, that's how we name a circle, so that makes BD a diameter, and it intersects chord AC at a 90-degree angle, which means we're going to use that second theorem. It was 10.5, the converse of that theorem, to say, okay, since this is the diameter, intersects the chord at a 90-degree angle, that means these segments right here are going to be congruent, which means CF is going to equal 7. And if we use our segment addition here, since we want AC, we would just do 7 plus 7 to get that the whole segment is 14. And again, that is using the converse of that theorem we were just talking about. And that's going to be the more typical type of question we're going to see with this. So less of the thinking about it word problems where you have to draw the picture, more can you apply the theorem. So why don't we go ahead and let you guys practice this a little bit. Pause the video and try this one on your own. Okay, so we are going to find the measure of the indicated arc in the diagram. So to start here, I see that this is a 90-degree angle intersecting a diameter because it goes through the center. So I know that these pieces right here are going to be congruent. So if I want to find the length or the measure of arc CD, well, if these pieces right here are congruent, that means these arcs also have to be congruent. So I know that 9x equals 80 minus x. So since these pieces are here congruent, that means those arcs are also congruent. So I can set up this equation right here to solve. So I can add my x over to get 10x equals 80, divide by 10 to get x equals 8. And that's not what it's asking for. It wants specifically arc CD. So I can just plug it back into there and get 9 times 8 equals 72 degrees. And then moving on, that makes my life a lot easier moving on to finding the measure of arc DE, because I know, again, it's congruent. That's how I set that up. So if CD is 72 degrees, that means arc DE will also be 72 degrees. And last but not least, arc CE is this entire arc right here, CE, the whole thing, which basically means I just need to add CD together, which I know is 72 from the first part, plus DE, which is also 72. So 72 plus 72 gives me that the entire arc CE will be 144 degrees. And again, these are your more common type of problems you're going to see. More straightforward, more just set up something and solve. So we have one more theorem to go over in this section. And it says that in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. Again, equal distance means congruent pieces. So again, things are congruent and two chords are congruent if and only if they're equal distance from the center. So looking at this picture right here, the chords we're talking about, are they congruent, would be chord AB and chord CD. And we would be able to say they're congruent if the distance from F to E was congruent to the distance from E to G, which we will figure out is true in different types of examples. So take a peek at this example here. In the diagram of circle C, QR equals ST, and they're both 16. They want us to find the length of CU. Well, using that last theorem, we know, well, if these chords are congruent, these have to be equal. So we can just set up the equation 5x minus 9 equals 2x. We can solve a little bit here. We can subtract our 5x and get that negative 9 equals negative 3x. Divide by negative 3 to get that x equals 3. And since they want us to find CU, I'm going to plug it back in, so we get 2 times 3 equals 6 for our final answer, and that equals CU. And again, lots of things are equal to each other that we're seeing in this section here. So we have one last little practice for you guys to try on your own. Number 8 is actually kind of a challenge, so see if you can figure it out and come back when you're ready to check your answers. Okay, in the diagram in example 4, suppose ST equals 32 and CU equals CV, and they both equal 12. So I kind of recopied the picture down over here and changed our measurements. And now let's work on these examples. We want to find the length of QR. Okay, well, these segments right here from the center are both equal distance, right? They're both 12. And we know using that last theorem that, well, if the chords are equidistant from the center, the chords are congruent. So since these are both 12, that means this guy has to be 32. And that's just using that theorem. Number 7, QU So that's this guy right here, QU. We want to figure out what that is. Well, it's half of 32. So we would do 32 divided by 2 to get 16. And we know it's half because this is going to be a perpendicular bisector. That's kind of going back to the earlier theorems we were doing. And the last little bit here is the radius of circle C. This one's a little bit more challenging, so it's okay if you got caught up on this one. A radius is any segment connecting the center to the edge of a circle. So I'm just going to draw in a radius here because we don't have a complete radius yet. But if I draw the line connecting circles center C to point S right here, I just drew in a radius, and I also created a right triangle. And before we knew that this was a bisector here, so we know that this also bisects this, so that small segment right here would be 16. I'm going to go ahead and redraw this triangle off to the side. Here's C, this is S, and there's my right angle. I know this right here is going to be 16, and I know that this small piece right here is 12. Well, to find the radius, I just need to solve for the hypotenuse, so I can use my Pythagorean theorem, a squared plus b squared equals c squared, and do 12 squared plus 16 squared equals x squared, which is 144 plus 256 equals x squared. You guys remember doing this from chapter 7, I believe. So this is going to give me 400 equals x squared, and my last step would be to take the square root of both sides to get that x equals 20, and that would be my answer for number 8. So again, that one was a little bit more challenging, but that's just kind of seeing how all of this gets put together with everything we've learned so far this year. So hopefully you guys followed along with that okay. Here's your homework for this assignment, page 657, number 3 through 13 odds. Again, they're the more straightforward problems, so email me if you have any questions.